Welcome to Bitlemmas, episode 22. I am here with B Sovereign. I'm Watson, and we're also here with Jose. Today is a book review of Patterns of Distributed Systems by Unmesh Joshi. Distributed systems are a pattern language for surviving partial failure. The point is to see which pattern alleviates which failure. The standard story says if you need scale, add servers. If you need availability, replicate the data. If you need speed, read from followers. And if you need transactions, add a coordinator. Joshi makes that story a bit more nuanced. Every obvious distributed systems fix creates a second order problem. Replication creates consistency questions. Follower reads create stale read questions. Partitions create metadata questions. Coordinators create recovery questions. So this episode is about the guarantee layer. What does the system actually promise when machines, messages, clocks, and membership are unreliable? So, what is this book about? It's a pattern language for distributed data systems. It's a code grounded tour of replication, partitions, clocks, leases, gossip, and consensus. We'll talk about all of these. It's a warning that adding servers also adds new ways to fail. It's a bridge from algorithms to production mechanisms, and it's builder advice for state, failure, and membership guarantees. We're going to be describing all of these. What's the thesis of the book? Distributed systems are best described as using a pattern, or best described using a pattern language for surviving partial failure. We'll talk about partial failure. You can't coordinate state without reliable timing, delivery, or membership. You should make hidden guarantees visible. So that's durability. We'll talk about that. Ordering, quorum, freshness or liveness, and recovery. And also, it asks a hard question. What does the system guarantee during partial failure? Now, major premises of the book. Physical resources cap single server throughput. This is one of the reasons why people want to add more servers. Stateful distribution is harder than stateless distribution. Why? Because you need to coordinate. We'll talk about that too. Acts or acknowledgments, logs, terms, and quorums define when a right is real. And we'll talk about consistency and why that matters. Reads need freshness guarantees, not just another replica. So if you are into databases and you add a bunch of extra followers and you think that that's going to make it easy for you to handle throughput, you have this problem of freshness guarantees. Membership, so that's who's part of a quorum or who's part of a cluster or what have you, and time are part of the correctness. These are all difficult things to deal with. Now, four counterintuitive truths. Truth number one, more servers create more coordination work. Why would you need to coordinate? We'll see. Truth number two, replication is not a guarantee until commitment is defined. We'll see what that means. Truth number three, quorums buy safety. We'll talk about safety, but it's basically a guarantee of correctness by charging throughput and latency. By you're having to pay the price of both of those. And then truth number four, time is a protocol decision and is not about wall clocks, which is quite counterintuitive to people coming from the outside. So truth number one, more servers create more coordination work. What does this mean? A single server, of course, you're limited by the bandwidth, CPU, memory, and disk limits. This is when somebody says, oh, we'll add another server. So you can think of web servers with a server farm, and those are all reads. So if you have a static website and there's a lot of people hitting it, you can add another server if you want. You can make your one server bigger, beefier. You can add multiple, and now you can split the traffic between the two. Stateless work can move to another node. So things that don't need to coordinate caches, you don't have to deal with any type of coordination. Stateful data. So if you had some type of indicator or if you're logged in, these types of things, it needs to, all the servers need to know to some extent. So stateful data has to be partitioned. What does partition mean? Partitioning data, you can think of think of the alphabet, so 26 letters. You can think of 26 nodes or servers, and you could say, I want to partition the data. So everything that begins with A, I'm going to do it alphabetically. Everything that begins with A goes on the A server. Everything that begins with B goes on the B server. Now you partitioned the data. And so you have one of the benefits of that is the B server is not serving any of the A server's data. So you're spreading the load. And or replicated. What is replicating? So that means you're having all of the data on more than one server. Why does that matter? Well, again, you can have it to where people will go to what's called you can call it a follower. So you have a leader and it has all of the data and the follower replicates the data. And you can send a subset of people or users over to the follower if all they're going to do is read from it. So these are some of the tricks that people have used to distribute. And off the top of my head, I'll give you one of the architectures that was really cool at the time. I want to say 2009 or 10 or something like that. YouTube. They made YouTube was started by a bunch of people literally in the garage. They had servers in their garage. And how would they, they're serving everyone's videos. How will they make it to where the database doesn't go down? Everyone connects to it all at once. And they did partitioning. They did what is called sharding. And they took a regular open source database, MySQL, and they made it to where they could shard it. They even made it into an open source project. I forget the name of it. So that's old school sharding. Now, more machines increase failure probability. What does that mean? Failure. So we're going to talk about partial failures and failure in general in multiple different ways. Why do you care about that? You can fail in my YouTube example. You log into YouTube and you have videos on YouTube. You're not going to like it if your videos you upload and they disappear. You might not have a backup. So how are they going to handle hundreds of millions of people uploading videos and all that? So they go off of that. You could think of it in a naive way. They shard, and all the people that last name begins with A go on one server. You can think of it that way. But what about if they fail? So you lose your data in different ways, or your updates can go in out of order. There's all types of things that we call consistency within the data parlance. So there's many different ways to fail when you have a distributed system that cares about state being the data that needs to go across and be correct across servers. So now if you're handling a stateful system, your job now is to mask those failures, to deal with those failures, to deal with partial failure without exposing inconsistent state.
All right. So a slight little recap here is and this is really the intuition break here. Distribution does not remove limits. It moves them. So a single server hits physical limitations in regard to bandwidth, CPU, and memory. Stateless work can move to another node easily, but stateful data, the stuff that actually matters, the stuff that users care about, must be partitioned and replicated. And once you do that, you've increased the number of things that can fail independently. More machines means more failure probability, not less. The new job is to mask those failures without exposing inconsistent state. So we can see this in Bitcoin's own history, right? The block size war, we reviewed it in episode 4. It was fundamentally about this trade-off. Bigger blocks process more transactions per second, but they make it harder for ordinary users to validate state. You're not removing the limit, you're removing it from throughput to decentralization. So the hidden product after distribution is coordination. The rules that decide state, failure, recovery, and membership. So that's the thing that you're actually building.
All right, so talking about the scale path again. How do people, when they decide to make something distributed, how does that evolution happen? So first, they have their single server. They hit the physical limits. They have their, you could say, the web server. Then they go ahead and let's have a server farm, multiple web servers, and it's stateless, so we're all good. Then you have a stateful tier. How do you deal with that? So every time you connect, why is that a bottleneck? It's because if you need to do an update, then you have to wait for all of those servers to come back with a yes, or you have to do some type of coordination to come back with a yes, I updated. So you can have consistency if you're going to guarantee correctness. So the stateful starts to have, and we'll talk about all the other issues that come with stateful later, but starts to become a bottleneck. It makes things slow, all of this stuff like that. Then you go into partitioning, like I talked about earlier with YouTube, where you can shard or separate data. Then you have replication, where you have multiple nodes serving up the same data, and you're going to have to deal with when failure happens there on both of these, partitioning and replication. And then coordination becomes the product, meaning the value you're bringing to the table for your system is your capability of coordinating and doing all of these guarantees that we'll be talking about. Now, truth number two, we're going to get a little bit more technical here. Replication is not commitment. What do we mean? A log entry, we're going to talk about what a log is, appended locally can be overwritten. Why does that matter? That matters when you're dealing with leader-follower dynamics. So let's talk about what a log is in the context of this book, The Patterns of Distributed Systems. You can think of a log as just a chronological list of actions in this context of thinking of a log, like a numbered sequence of notebook pages. So you could think about it as, you could say, a teacher and the students, multiple students in a classroom, and the teacher is giving a lecture and the students are taking notes. The notes are the logs, the notebooks are the logs. So a leader can fail before a majority receives the entry. What do we mean when we're talking about leaders and followers? And we're going to use this analogy with the students. So, and then we could also talk about the followers can have divergent log prefixes. So this replication log, this write ahead log, there's a bunch of types of logs for dealing specifically with distribution and trying to solve the problems of distribution. But so we're going to go back to the analogy of the teacher and the students. So what's a log prefix? If you're thinking about the teachers and the students, the first part of the student's notebook up to a specific page number, that would be a log prefix. So you could say, and we have a diagram on the next page, but you could say page 1 through 4 of each student's notebook. So all their pages 1 through 4, that's the log prefix. So you can have divergent log prefixes. What does that mean? So if you can imagine all of the students, they are writing the teacher's notes, and the teacher says, they're on page 4 and the teacher says blue, and one student writes down blue, so that's student A, and then they write down on page 5 green. So he's writing down what the teacher's saying in a log. The student B on page 4 writes something different, whether they heard something different or they just had an error, they write down red. And then on page 5, they write yellow. That is a divergent log. And you're thinking of the students writing in their notebooks. So now, again, we're going to have a diagram on the next page. There's a concept of a high watermark in the log for trying to solve this problem of replication. The high watermark would be where the last known correct stage was for all of the notebooks. So if page 3 for all of the students, they were all the same up until that page, that would be the high watermark. And then, so that's safe. And only what's safe should be visible to all the clients that are consuming what, in this case, what the students are writing. Why does that matter? This is a guarantee of correctness. So when you need to guarantee correctness, you're going to have something like the replicated log, leaders, and all the stuff that we're going to be talking about. in order to do those types of guarantees. Here's what a replicated log looks like. Again, you can think of the students' notebooks. Page 1, page 2, page 3, those are all safe. The high watermark happens on page 3. Then page 4, 5, 6, you have failure, whether between two students or all the students. So how this is a failure. You can call it a partial failure, full failure, whatever you want. Now, you also have how the high watermark and all the dynamics solve or try to provide these guarantees that come with this setup. So you have the leader, which is using a log called that WAL's write ahead log. So that's where everything starts, and you're having this communication between. You can think about it with the students. So a client sends a write request to the cluster, you could say the students, and the leader, this teacher, receives it and assigns a sequential index number. We're going to talk about how you do sequential things and all of this, and writes it directly to its own write-ahead log, the WAL. So at that point, that entry is in the tail, which is uncommitted and not yet safe. So we're talking about how leader dynamics work, and we're going to talk about it again. Then you have the followers. The leader immediately broadcasts the new entry, again, broadcasts to other nodes, which are the students here, a new log entry to all the followers in the cluster. So teacher to student. Each follower is instructed to append the exact entry at the same index position in their own local logs. And then you have a quorum. So a quorum is like a vote within a set of nodes. The leader waits for the followers to send back the acknowledgement, and in this case, it's the students sending back acknowledgement to the teachers, and they're saying, "Hey, I successfully written this to my disk." And then once a quorum, so that's a strict majority of the nodes in the cluster, including the leader, responds with the acknowledgement, then the leader advances the high watermark, and that high watermark is what everyone can treat as a kind of guarantee.
So I think the lesson here for builders is that logs are not magic in any sense. The lesson is that every write needs a visible path from local intent to committed state, and that path must be idempotent at the receiver. And idempotent is the property. I found this out while reviewing for this book, actually, is the property of an operation where applying it multiple times produces the same result as applying it just once.
So now we just went through this, the commit boundary. You have the client writes, you have the leader logging the intent, the followers replicate, the quorum defines the commitment, and the high watermark exposes the safe state to all the other clients. So now you have a guarantee. Now, truth number 3, quorums charge for safety, safety being some form of correctness. So majority decisions prevent split independent decisions. This is something that you want. You want to be able to stop that. And there's going to be a big risk if you don't stop that as far as data being corrupted. So you have 2 types of faults. And this is for the audience here. There's a traditional software development, but in the corporate where you're trying to increase throughput and availability, but you have the luxury of being able to have control of the nodes to the extent of they won't be malicious. So in those environments, you can adjust and compensate for what's normally called crash faults. So what's a crash fault? That's when a node either it can disappear or be unreachable or whatever, but it doesn't continue on doing damage, let's say. It's not doing anything malicious for sure. So when you're dealing with a crash fault, then there's a little algorithm that you can use as far as nodes when you're trying to figure out what the quorum needs to be. So the idea is you can double the number of failed and add 1, and then that will allow you to survive as far as when you're trying to make a quorum. That's the amount of nodes. So you can have 3 nodes and 1 failure, and you can survive. Byzantine faults are where 1 node can lie. 1 node can be malicious and is actively working against you. When you have a Byzantine fault, and when you need to adjust or compensate for Byzantine faults, then you need to triple the amount of failed. You need to have enough nodes to where you can triple the amount of failed to reach the quorum and add 1 to survive. So this would be where you need to have 4 nodes. One fails, now you can have 3 that are the quorum, but you can't do it with just 3 starting. Now, given that, there's also this property where if you have 2 majorities that overlap, the intersection carries the history. This is an interesting property that we're going to go back, but this is what allows you to get around what's called the split brain problem, which we're going to talk about later. So you can have a guarantee against the split brain problem if you have it to where 2 majorities always overlap. So you can think about if you have 5 nodes and you maintain that there's going to be 4 with a majority or as a quorum, then you're always going to have an overlap. Now, counterintuitively, again, another piece of this is that more replicas can actually reduce the throughput. Why? Because now you're having to get a quorum and you're going to have to get an agreement of the quorum. So even though you have multiple nodes before where you didn't, it was either you could say just stateless or you didn't care about the guarantees, anyone can go to any node and be happy. But when you need a quorum, now clients have to go to multiple nodes or the quorum has to be reached in order to have some of the guarantees.
And so for here, what I would say is, I mean, the message for the builders here is that you can always buy more safety by requiring larger quorums, but you pay in terms of throughput and latency. So there is no such thing as a free quorum.
So quorum intersection, again, like what I was saying here, now you could say you have 1, 2, 3, 4, 5, like what I was saying. And if you have a quorum of 4, you'll always be able to resolve conflicts and you won't run into this split brain problem. Again, the fault model. If you have a crash fault, again, on the left-hand side, you have 3 nodes. All you need is 2 in order to give some guarantees for that quorum so you can form a majority. But if you have if you're trying to cover Byzantine faults, you're trying to have guarantees versus them, then you're going to need 3 out of 4. So three matching replicas can outvote 1 liar. Now, what does Paxos look like? You ask for promises, and then we're going to review this a couple of times. You ask for promise, you prepare, you have an acceptors report, you have a proposer stage, you accept the quorum, and then you overlap. Your overlap, what we talked about previously, is going to handle split brain. So let's talk about an analogy given this Paxos. So imagine you're trying to get a big group of friends to agree on where to go for dinner, but everyone keeps communicating through texting. And some people have bad cell service, and different people keep proposing different restaurants at the same time. This, sounds like real life. Paxos is the set of rules that the group chat uses to make sure everyone locks in one final answer without throwing the group into total chaos. So here's how each step of Paxos works. So, number 1, you ask for promises. Before you suggest a restaurant, you text the group, hey guys, I want to make a plan. Ignore any older plans anyone has suggested before me. And so you're asking them to promise to only listen to you for that moment. Now, number 2, the acceptors report the prior accepted value. Your friends text back. They give you their promise, but they also tell you an update on what happened while you were away. They say, oh, I promised to listen to you, but by the way, Billy suggested pizza an hour ago, and we almost agreed to it. So that's step number 2. Step number 3, the proposer keeps the highest prior value. So if you find out the group was already close to picking pizza, you don't fight it, even if you wanted tacos. To keep the group moving forward, you take the most recent popular idea, which was pizza, and adopt it as your own proposal. Now, step 4, you accept the quorum record's chosen value. So now you officially text, all right, let's lock in pizza. And if a majority, which is a quorum, of your friends text back, deal, then the decision is officially saved and finalized. So that, in a nutshell, is how Paxos works, and is a thing for me. Reading about Paxos, I want to say when it first came out, but when it got very popular, I don't know if it was like 15, 20 years ago, it was super complicated. Paxos and another algorithm called Raft was actually pretty complicated for people to reason about, and but everybody was trying to implement it and trying to get all of these guarantees. So now let's go into time. So time is a protocol decision. TCP/IP, as an example, gives no guaranteed upper bound on messages. What does that mean? When you send a packet, there's a reliability guarantee. It can say, you as a client, you can say, when I receive the packets, after it's done, after TCP/IP has done its thing, I know that I got them in order. But TCP/IP itself doesn't have any guarantees of how long it'll wait for a packet or what have you. And I think this is kind of trivially true because, of course, a packet can just get dropped on its way out and it doesn't know how long it's going to wait. So that's one problem that leads into time and how long you wait for something. So on another stage, it can pause and later resume with old assumptions. What is this? So if you've been writing software and you use, let's say, Java, for example, and you're writing that are server processes that take a long time, there can be this long pause where the interpreter clears up memory. So they just call this garbage collection phase or pause. It can be a while. There are different algorithms for dealing with this garbage collection. Different languages try to deal with it in different ways, but it's a beast and it can take a long time. So what ends up happening is when you resume the old assumptions, some writes could have happened, all kinds of other things. And the process can turn around and think that everything was the way, the world is the way that it was when it stopped, and it's not. So how do people try to deal with it? They try to say, hey, if a bunch of time passed, go ahead and look at everything again. Go look, get one thing would be to go read all the data again. So system clocks, though, like the clock on your computer, can drift, jump, or disagree. So you could have a clock on one computer and a clock on another one, and they do not agree with each other. There's another type of clock. It's called a Lamport clock. And the way that the Lamport clocks work is they're based on causally related events. So when you do that, it allows you to reason about time in a way to where now you can handle some of the distributed problems. So let's go into what we're going to review this a couple times. But a Lamport clock, it's a logical clock in the distributed systems, and it's used to determine the chronological order of events without relying on synchronized wall clocks, physical clocks. How does it work? An algorithm assigns a monotonically, fancy word, monotonically increasing numerical timestamp to every event in the system based on some rules. So monotonically means just guaranteed to go in one direction. It's just going to go, in our case, it's just going to go up. So you can think of it as a counter if you want. So one of the ways that it's implemented is internal events. So you could think about a process is doing a bunch of commands, and it'll just say, hey, I did 3 commands. I added to the Lamport clock. So each process increments its own local counter by 1. And then these processes, so there's processes are like if you think of little workers on a computer, they can talk to each other, but you can also think of one node talking to another node, one machine talking to another machine. So when it's doing that, either between processes or between computers, think of it the same way. Message passing. When a process sends a message, it includes the current clock value, right? That little incrementer. And then when another process receives that message, it updates its own clock. Remember, we're talking about Lamport clocks, not wall clocks, to be greater than both the current value that it has and the received one. So it continuously adds. Now you can have one last thing is you could have hybrid clocks. So that's the wall clock and the Lamport clock together.
So yeah, I want to say like this truth is probably the most counterintuitive because it challenges the assumption that time is a fact about the world. In a distributed system, time is a protocol design. TCP/IP gives no guaranteed upper bound on message delay. Processes can pause, garbage collection, scheduling, virtualization, and resume with old assumptions. System clocks can drift, jump during NTP sync, or disagree between nodes. So the system cannot trust wall clock time by default. And here is the implication for builders. Which clock pattern you choose determines which ordering promise your system can safely make. If you're serving reads based on wall clock timestamps without bounded skew, you're making a freshness promise you cannot keep. So the hard part of clock bound wait is that it turns time into a capacity question. You need to know your worst case skew before you expose state.
So now let's review again how people reason about time when they're developing their software, and then they get more and more advanced. So you have the system timestamp. It's convenient, but it's not monotonic. So you're not going to be able to guarantee that time goes in one direction. Then you have the Lamport clock, which we just talked about, causal ordering, a hybrid clock. And then you have this more advanced clock bound wait, which is implemented in a paper about that Google released. I don't remember the name of the paper, but the software that they use is called Google Spanner. And so they combine the physical clocks with a small amount of uncertainty, like B. Sommer was talking about skew. And you could say, okay, we have a certain amount of uncertainty, and we're going to account for that uncertainty. And then that will allow you to have another level of guarantee that a transaction is truly linear, truly happens, and a set of instructions happen in incremental fashion, one after another. So that's yet another guarantee. So all of those are kind of the evolution people will take when they're reasoning about time, and they want to have better, and why they're reasoning about time is they're wanting to synchronize things and make it to where they have these guarantees and promises and so on and so forth. Two-phase commit. I'm not going to go too much into this, but again, this is where if you're trying to, again, going back to commits, it's easy, I say relatively easy to guarantee a commit, which is within database parlance. You have a transaction, you want to do these certain commits within a transaction. So if you can imagine, a bank transaction is the one everybody uses. So in order to do a proper transaction with the bank, you're going to transfer money. So if you subtract from one account and you add to another account. But what happens if you subtract from one account and a failure happens? And so they lost their money. The new account doesn't have the money. So when you're doing those steps, subtract from one and add to another, you want to wrap that in what they call a transaction. So you're wanting to have it to where you either commit those two instructions at the end and make it to where it's correct. You don't want to save if something happens. So if you subtracted from one and you tried to add to the other and you failed, you want to roll back, and to everyone else viewing, there's a bunch of properties I'm skipping over, but to everyone else viewing, it looks like the money was never, that's called isolation, was never removed from the first. That is just regular databases. Two-phase commit is when you have the network involved. So you have two machines. And so now you run into a whole other set of problems. So the preparer asks each participant to promise that it can commit. So you're talking about two nodes now. You got the network involved. The participants secure locks. So you're saying, I'm going to lock down a resource. And then they persist decisions in a write-ahead log. Remember, the write-ahead log is you're writing to your intent to a durable log, meaning it's most likely it's going to the hard drive, and before it goes into memory, and then memory, everybody shared, that's the shared state that everyone can trust and access. So any no vote forces a rollback. I just told you about what a rollback is. And then all yes votes allow the commit and visibility. So yes votes, we're talking about multiple nodes. The coordinator has to remember the outcome across crashes. All of this ends up being a thing that you really don't want to do very often, and something where it's going to require a lot of speed. Now, when you're trying to reason about big clusters where having, if you're doing things like two-phase commits and all of this other stuff, the speed is just going to be too slow for it to be useful. So large clusters cannot have a quorum on every node. Metadata has to be fault tolerant, able to withstand those crashes we talked about, regular crash, and if you're trying to deal with Byzantine, but be strongly consistent. So that strongly consistent, that consistency that I talked about earlier, say with the bank transaction, that would be a strong, consistent guarantee. You need that in order to, and we'll talk again the next couple, I think it's the next slide, we're talking about split brain problem. You need to have that in order to have any of these guarantees to where your data doesn't get corrupted, for instance. One of the solutions is you can have a small, consistent core that manages membership. What is membership? Membership in the quorum and the placement. There's this concept of leases. So what's a lease? You can have it to where you have a leader. Remember, the leader is the one that's coordinating everyone. And one of the problems is if you don't know who the leader is, the leader can disappear. Now you need to elect a new leader and all this stuff. Leases are a way you can have a time claim for the leader. And then if they don't respond in time, then everyone's able to agree without coordinating first. Hey, it's time for a new leader. And then you have watches that notify the nodes when membership changes. So this consistent core you can have to where you try to manage large clusters. Now, gossip's the weather report for membership. So people reach for gossip when they think about distribution. I'm just going to send the messages everywhere and we'll be fine. There are some things that are great properties of gossip. So random fan out, you call it gossip, spreads metadata without flooding. So you can not send to everyone, you can send it randomly. And one of the properties is it's like a virus. It spreads really fast to the cluster. Few contexts can converge cluster-wide, speed-wise. You can have version values that send only change state. So that's a way of making it to where the data can move forward. Gossip tolerates loss, but remains eventual. Eventual meaning what? Eventual consistency. Eventually, everything can be correct, but you're not going to know when. Strong decisions still need a consistent core, what we talked about previously. Now, for the beast, I will say, again, like 2010, 2012, so around there, people were doing distributed programming and they were having all of these data solutions and they were coming up with different consistency guarantees. There were papers written all over the place. But one of the things that came through and invalidated a lot of models was this problem here, the split brain problem. So when you have within a system two sides that separate and continue on their merry way, and then they try to come back together, that's the split brain problem. So partial connectivity can form subgroups, and each subgroup can decide that the other side failed. Then you have two coordinators. So they each formed a coordinator and they can make incompatible decisions. Minimum members checks let the majority keep on serving. So the minority must stop, merge, and rejoin deliberately. Well, what are the implications of this? Corrupted data. You come together and somebody has to win. So everybody else, one side loses all their data, let's say. Or there's some weird merge where you're having corrupted data. Or you're never able to merge back again. So this problem here is one of the reasons why Paxos exists and another algorithm called Raft. So that it's really an algorithm. That discussion we had where people were deciding on whether they should get pizza or tacos, that's Paxos, and that solves the split brain problem. But people weren't thinking about this at one point, and they were doing distributed systems. Why? Because they wanted the availability and other properties, and then they were causing tremendous problems. So, what's the hard version of the claim of the book? Safety, that's correctness, guaranteeing the correctness. And liveness, what is that? That's a guarantee that the system will progress to some solution, that it's progressing, are both real and can conflict. Not only can they conflict, basically, there's an FLP proof that basically you can't have both. You can't guarantee both. Paxos chooses safety before liveness. So it's going to have the correctness instead of the liveness. Live lock, so you have deadlocks. That's when you have a node, two nodes, and they cancel each other out and they stop. Okay, that's one problem. They're dead. But live lock is you have two nodes and they just keep thrashing. You can have a live lock being reduced by some of these algorithms, but not eliminated as a guarantee. So you can't guarantee that it's going to progress to something useful. FLP is a proof that says one faulty node can prevent decision in a fully asynchronous case. But basically, you can't have safety and liveness. So the honest interface says what the system may refuse to do. Now, here's an argument of the book, and we'll get into our critiques. So, argument: state under partial failure. If state crosses unreliable machine boundaries, whenever you touch the network, it's unreliable, then coordination rules are needed for that state to be correct. If different coordination rules combine to exhibit guarantees of correct commits, freshness, membership, and order, then those coordination rules become named patterns. This is what the author is reasoning about and trying to make it to where it facilitates a vocabulary. Successful distributed systems are best described using a pattern language for coordination rules that survive partial failure. Again, the whole concept is surviving partial failure. If you're trying to do distributed systems and you don't have a way of surviving partial failure, then you're going to have all kinds of unruly problems. This is a part of the presentation where we talk about how we critique the book. So this is software craftsmanship and applying it to the domain jargon of distributed systems. So what we're going to do is talk about language, which the author, it's interesting because the author is borrowing from one of the ways that we normally critique all of our books, the pattern language. So there are three books: The Structured Interpretation of Computer Programming, The Timeless Way of Building, Christopher Alexander. This is where within software, all of the patterns community gets their influence from Christopher Alexander, which is where this author gets their influence. And then we have Eric Evans' domain-driven design, but really what we're borrowing from there is the ubiquitous language. So the idea is you create a language to facilitate people making an architecture from the bottom up, and then you critique the language. So now, how do we critique this language, this domain jargon that's in this book? You have primitives, you have the fundamental methods of composition, and the fundamental methods of abstraction. What is that? The primitives of the book: nodes, logs, versions, partitions, leases, clocks. These are all things that are inside of the book. The fundamental methods of composition: how does the author say you should compose those primitives? The write-ahead log, plus the leader, follower, plus a quorum, plus a high watermark. We talked about that. That's a way of doing some type of quorum, coordination, leader election, these types of things. Those are valid compositions. Then you have fundamental methods of abstraction. What's that? These are the workhorses within a domain. Commitment, freshness, membership, and recovery. These, you can look at these as kind of meta compositions, but these are the workhorses. These are the things that you want to reason about. You want to use these to solve the problems within it. So what with the ubiquitous language, trying to forestall talking past another person when you're talking about distributed system, you want to name failure and guarantees and say these are things that we care about and within this domain, within this problem domain, before you even choose a mechanism of solving those problems.
Now for the exit and choke point analysis from the framing of the author and the context of this book. So first, we're going to start with the choke points, right? The leaders, coordinators, and consistent cores are where every commitment, membership, and metadata decision flows. If they are hidden, users cannot diagnose failures. The choke point is not just a performance bottleneck, it is an epistemic bottleneck, to say the least. So, what we should do is name the commitment boundary before exposing state to clients. If users can't see what is committed, they can't know when it's safe to act. The commitment boundary is the first thing that must be legible. Second is freshness degrades silently. The system keeps serving, it just serves older state than the client expects. Naming the freshness guarantee is the only fix because the failure is invisible until someone acts on stale data. So, what should we do? We should make freshness, retry, and partition behavior visible in the happy path. Don't wait for an outage to reveal what your system guarantees. Put it in the interface where users can see it every day. Third is the third choke point here is availability during partition can leak impossible data, impossible state. Staying open risks conflicting writes, divergent logs, and corrupted state. Fail closed is the safe default, and most systems choose the unsafe one because downtime looks worse than silent corruption. And so for here, we want to treat membership and time as correctness variables, not operational details. If you treat them as ops trivia, you'll make decisions based on a fiction. They are part of the correctness argument, full stop here. For every exit path, retry, redirect, degrade, and fail close carries a different safety availability trade-off. Retry can double execute, degrade can serve stale data, fail closed preserves safety but cost uptime, and these are not implementation details. They are part of the architectural choices that determine what your system is. And for that, we want to choose fail closed defaults, refusing to serve beats, serving impossible state. Availability that serves conflicting state isn't availability, it's corruption with a friendly interface. So for our fifth here is that the fifth choke point is the guarantee surface is the governance surface. If users can see commitment, freshness, retry, and partition behavior, they can make informed risk decisions. If they can't, they are governed by a system they cannot inspect. And that is the definition of captive participation. Publish the guarantee map so that users can diagnose before the outage, not during it. The guarantee map is the governance surface. If it's hidden, users are captive to a black box they can only inspect when it essentially is broken.
So now, to onboard early adopters, and you're trying to use this jargon, you're trying to use these patterns to build something that other builders or users, but in this case, most likely builders, are going to adopt and use. You want to have as little friction as possible. So this would be builder usability. One of the things we want to do is to make the guarantees visible, like B-Sarmer was saying. So you want to expose the state guarantees in the happy path of the frameworks that you're building. And you're trying to get people to reason about these state guarantees. Convention over configuration. You want the default consistency, the way that you do retries, and how you do your fail close behavior. You want all of these things by default, the default configure, the default convention, I should say, instead of having it to where they go in and they configure it. Another way to look at that is you can think of it as going into a restaurant and having the chef recommend the meal of the day in the way that he or she prepares it. When you're making a framework and you are the one building the framework, one of the things is like you want to make it to where it's kind of like a one-click install for the people to get going. Within this domain, that would be writes, logs, quorum, visibility, and recovery. All of those things having a default setting that people can get started with and be cognizant of the trade-offs that they are getting. When you're thinking about how you're onboarding the users, you want to test if the users can identify freshness, commitment, and failure. Again, users could be users of your framework, so they're builders. And that would be like a minimum viable product for your framework. You want the visible guarantees. You want to understand that visible guarantees beat hidden distributed magic behind the scenes. So you don't want to have it to where you're doing all of these guarantees and you're not educating your user base on the big trade-offs that they're having. So some questions to contemplate when you're thinking about these distributed systems, building them or using them. So what state is exposed before the commitment? Which reads are stale tolerant? Read your rights. That would be where you, as a client, you have a leader and you have a bunch of followers. And one way to do read your rights is you could have it to where you read from a specific follower, and that's fast, and you only are reading from that one follower, but you also write to, you could have, there's all of these configurations. You could have master, or leader, and all this other stuff where you can do your write. You, in a distributed system where you do a write, it's sticky, and you never write to one. You do a write to one node, and then it flips, or you get directed to another node and you do a read. No, you stick to the same one that you wrote to. That's a read, you write, or leader backed. Understanding these parts of the distributed system. Who decides membership during partition? Again, reasoning about Paxos and Raft and all of these things. Which retry can double execute? So that would be the idempotency that B. Sarvin was talking about. And can users see the safety preserving refusal characteristics? Now, conclusion: distributed systems are a pattern language for surviving partial failure, or they're best described that way. More servers do not remove the limits. They move the hard part into coordination. Replication becomes useful only when commitment is named. Quorums, clocks, leases, gossip, and coordinators are guarantee machinery. And the builder question is, what can users trust during partial failure? So if you only take one thing away, it's distributed systems are a pattern language for surviving partial failure. More servers do not remove limits. They remove the hard part, or they move the hard part into coordination. Replication becomes useful only when commitment is named. Quorums, clocks, leases, gossip, and coordinators are guaranteed machinery, like we said. And really, for builders, what makes that guarantee or any of these guarantees visible before users have to reverse engineer it from an outage, let's say? And what can users trust during partial failure? So as always, leave any feedback in the comments section at bitlemmas.com. You can also visit bitlemmas.com for more information and past episodes. Thank you, and we will see you next time.